Okay, in this video we're going to see a simple way to impose bounce back boundary conditions on a set of particles. Let's see, we have 100 particles, number of particles, and let's set some position, part pose, goal, run 2 to m, where first row is x component and second row y. Well, I would like to center the distribution of these particles. I multiply it with 2 and subtract 1. What we have here is a set of particles, because this is uniformly distributed. What we're going to have can be seen here. Particle positions onto all, particle positions 2 to all. And we can see here these particles are distributed uniformly between -1 and 1. Now let's go ahead and add velocity to these particles. And in a for loop, you're going to move these particles. Particle position equals particle position plus delta t times particle velocity, where let's set delta t equals to 1 and let's say draw now to see how these particles are moving. Okay, to see this easier, let's fix the axes. Minus L to L, minus L to L. L is our box half width, and we just multiply it here. Okay, this was probably too fast. We need to reduce the delta t and close all. Okay, we can see how our particles are moving. What we want to do is impose boundary conditions in these boundaries. After each movement, we check with a function called BBBC if the boundary is breached and how the velocity is changed. This function is particle position, particle velocity, and the boundaries, where the boundaries are, and it gives out particle position, particle velocity. Okay, for this case, I'm going to copy all of this over here, make it a function. Well, now you need a loop that checks which particles have crossed the boundary. Well, now particle position bigger than L is the particles that crossed the boundary. But to make things easier and make the code more usable, I will only check the plus y and minus y. You will see in the end how we can introduce it for plus x and minus x. Okay, now let's see. I would like to use this as a script until the end of the code to check if everything is working correctly. Just finding some particles. I will assume that it is correct. After finding particles will breach the boundary, what we want to do is put them back on the boundary. So to do that, what we do is find the time that passed out of the boundary. So it is absolute particle position in y direction minus L. I only want the particles who breach the boundary, which is defined by loop, over particle velocity of the particles who breach the boundary. And you see here, I use dot to divide individual elements in the matrix. Well, after finding the time, what we do is we move these particles back to the boundary. Particles minus delta t after times particle velocity well, let's not get confused here. You find only the particles who cross the y boundary, and you move all of the particles. I mean, in all of the directions, because we need to move the whole particle. After this line, particles are on the boundary. Now, you need to move these particles. You need to invert their velocity. We actually need to invert the velocity only in the y direction, which is minus part vel to loop. Now we need to move them just this much. Here's a tiny problem. This is a vector. The other one is 2 by m matrix. Let's see how this works. Okay, dimensions must agree. I forgot the loop here. You can see particles are bouncing off of the y boundary. Well, let's now make this a function. And we're gonna go see if this is working this way. What I'm seeing is These are bouncing off of the upper boundary, but not the lower boundary, which is interesting. Okay, our mistake in here is we should have divided by the absolute value of the velocity, because we're just looking for the time, and if we don't divide by the absolute value of velocity, we could have gotten minus time, which is not what we're not interested in. Now let's run our simulation. I added some changes in here. Okay, now we can see they're contained in Y. What we can do is, let's see our box. Let's put a rectangle in here. Rectangle, position, minus L, 2L, 2L. As far as I know, this is how we draw a rectangle. Hold on. Put a clear figure in here. So they are contained in Y. So let's make this we can just contain them in Y, or we can just run this twice and contain them in X with a little trick. We're going to flip the position up and down, and velocity up and down. What we get is the flipped position and flipped velocity. Now we're just going to flip them again. Flip particle position and flip particle velocity. Let's see if it works. Had a nice clear figure. Okay, so this is how we impose bounce back boundary conditions. In the next video, we're going to see how this vectorized code speeds up compared to a loop code with many for loops. This may look a little bit confusing. There are no if or for loops, but yet this should be way faster than a non-vectorized code.